All right, so unfortunately, I've lost access to my blackboard, or my whiteboard, I mean. So we're going to have to do things a little bit differently for this last lecture today. So the last thing you have to deal with is turbines. So turbines are essentially the opposite of pumps. Turbines extract energy from the fluid as opposed to pumps, which put energy into the fluid. So for pumps, you have the rotors in the pumps spinning around, adding energy to the fluid. In this case, the fluid's coming in, hitting the rotors, and that's what's making them spin around. So that's taking energy out of the fluid, putting in some sort of shaft work. There's two types of turbines, impulse turbines and reaction turbines. The difference between these guys, impulse turbine, so again, fluid comes in, hits the blades, that blade, or that fluid, I mean, changes direction. That change of direction is what causes the blades to move. So it's essentially almost like a tennis ball coming in, hitting a wall and being rebounded back. That's kind of what's happening here. Fluid's coming in, hitting the vane, being pushed in the opposite direction. So coming in and out at the same speed. And that change in direction is what causes the force, causes the shaft work. In a reaction turbine, you have both. You have a change in direction as well as a change in speed. So the fluid comes in fairly fast. And then as it hits the blades, it not only changes direction, but also slows down. So it extracts a bit more energy out of it that way. So it's something called the degree of reaction, capital R, which is the ratio of the drop in static pressure or enthalpy. So again, if I have a pressure change, if I have a velocity change, that's going to lead to a pressure change. For an impulse turbine, I have no velocity change and therefore no pressure change in the fluid. And so for an impulse turbine, R value is 0. For reaction turbines, I do have a change in velocity and therefore have a change in pressure. So typically, R values for that are between 0.1 and 0.7. So what I want to look at is the total head coming in. So going back to Bernoulli's equation, each side of that represents the total head. You have pressure plus a velocity term plus an elevation term. That's basically three components of Bernoulli's equation. That's your total head. Basically, you want to convert that to some large velocity. So you have some pressure, 0.1, some velocity of 0.1, some elevation of 0.1. You want to turn that into some really big velocity, V2, coming out, because that big velocity is what's going to actually hit the turbine and make it spin. So the more velocity, more energy it has, the more you can get out. So generally you have a small pressure drop and change of velocity across the vane, especially with impulse turbines. So again, velocity doesn't change. Space surrounding the rotor is not necessarily full of fluid, and the impulse of the individual jets creates a torque. Again, that's the fluid coming in, hitting it, and being basically rebounded back in the opposite direction. So these are generally high head, low flow rate devices, so not much fluid moving through them, but come from a significant head. A lot of what happens from that is like a water wheel. So the head is like an elevation. And so for water wheels, generally given on rivers or down waterfall type things. And so you have this really large difference in elevations causing that rotation. So here you go, picture my water wheel. So again, I have some velocity coming in. That velocity hits these what are called buckets or vanes. And because it hits those buckets, it pushes it, and pushing that turbine, it's going to make it spin around. And then that is attached to some shaft, and you get some shaft work out of that. So here's another side view of it. So again, I have some nozzle, really high velocity coming out of here, hitting those buckets, making the same spin around. You can work out of it. Technically, this is neither radial or axial flow, but rather tangential flow. These guys are most efficient at high head, like I said, have some elevation gain, and that's converted to some large velocity as it hits my water wheel. So again, if I have some sort of waterfall coming down here, that water is going to have fairly high velocity when it hits this water wheel, and the higher the velocity, the more work I can get out of it. So some design considerations for impulse turbines. You want to look at head loss leading up to the entrance. So if there's a lot of friction after that waterfall, you kind of want that water wheel close to the waterfall so that there's no way for the fluid to lose energy before that. The design of the nozzle, so again, how are you going to shoot the water the most efficiently onto the vanes, as well as design of the buckets or blades on the rotor. So again, how do they basically trap as much energy. You usually see them kind of hollowed out. That's why they're called buckets. They kind of trap as much water so that you get more energy out of the water that way. And again, ideally, you want fluid to enter and leave with no radial component velocity. In other words, when it comes in, basically comes in, hits the vein, the most efficient way to get energy out of it is for that water to go straight backwards. Again, kind of like a tennis ball hitting a wall. As it hits the wall, it gets rebounded exactly opposite direction. That's obviously not possible with these impulse turbines because the water is coming in. If it got rebounded back in the exact opposite direction, it would hit the water coming in, and that obviously can't happen. So ideally, that's what you want to have happen, but not physically possible. So you kind of want it to have as small an angle in here as possible, or in other words, you want this angle beta to be as big as possible, up to 180. But obviously 180 is not possible, so whatever the biggest value before 180 where it doesn't actually hit the jet coming in. That's what we're looking at. And so we're going to look at this again in terms of the same kind of velocities we had before. So V1, absolute fluid velocity coming in. I have U1, the velocity of this bucket or blade itself. W1 being the relative velocity, so relative fluid velocity compared to this bucket. So V1 minus U is W1. Same thing for W2. In terms of magnitude, same speed, so W2 is W1. So magnitude-wise, it's still V1 minus U. So looking at these relative velocities, like I said, so this is the incoming stream. I have some total fluid velocity V1. That's a combination of the bucket velocity U1. So remember, this bucket's spinning around as the water's hitting it. So it has some tangential component of velocity, U, which is just the, again, radial speed times the radius. Rotational speed, omega, times r. Then there's some relative fluid motion, which is, again, the difference between those two guys. And then same thing coming out. So coming out, I have this W1 going back at some angle. I'm going to call it beta from the incoming fluid. I still have this velocity U, which is the same as my velocity U over there. And then my V2 is the combination of those two guys. So W plus U using my absolute velocity, just like it did before. So we can see from the previous picture, or this picture that's still down here, my theta component. So in this case, the theta component is basically X and Y. Because again, I'm assuming I have this big water wheel kind of up here. And so down at the bottom, my tangential component is straight left and right. So I want the basically X component of this guy. So V2 in the X direction is just W2 cosine beta. That's the X component of W2. U is in the X direction, so W2 cosine beta plus U gives me the X component of V2, which is what I want here. Then again, assuming W1 and W2 are the same, look at this equation for V2 theta and this equation for V1 theta, and knowing that W1 and W2 are equal, V2 theta minus V1 theta, so this guy minus the other guy. So here's V2 theta, W2 cosine beta plus U, minus the one we had before, which was V1, because V theta 1 is just V1, X direction. So W2 cosine beta plus U, and then V1 is U minus W1. So just put that back in, the U's cancel out. I have a W2 cosine beta plus a W1, but W1 and W2 are the same thing, so I can pull it out as W1 cosine beta minus 1. And then that gives me, again, W1 is V1 minus U. So V1 minus U, cosine beta minus 1. Why is that not plus 1? All right, so try that again. V1 is U1 plus W1. So when I minus V1, I should subtract U1 and W1. So this should actually be a minus sign. Minus sign in there. There we go, that's better. So W2 cosine beta minus W1, which is W2, same thing. So then pull that out, and I get cosine beta minus 1, like I showed down there. So back on track. Conservation of angular momentum, same as before. Shaft torque is stuff coming in, m1 dot r1 b theta 1, stuff going out, m2 dot r2 b theta 2, and then b theta 1 and b theta 2. I can use, again, those relationships from what we just had, plugging those all in. M dot, m1 and m2 are the same. R1 and R2 are fairly close to the same thing. So what we can do is basically just call that Rm, distance to the center of the jet. Technically, R1 and R2 are slightly different, but it's close enough to Rm, kind of the average of R1 and R2. That gives me close enough value. Then it's just a matter of v theta 1 minus v theta 2, which we know from the previous slide, is u1 minus v1, 1 minus cosine beta. And then my shaft work is just the shaft torque times the rotational speed omega. So just add another omega onto here. Omega times Rm is just my blade speed u. So there's my equation for the shaft work for an impulse turbine. So both power and torque functions of the angle beta. Maximum is going to occur for 180 degrees because I have this function that's 1 minus cosine beta. Cosine 180 is -1. So 1 minus -1 gives me a 2. So that is the maximum value I can possibly get out of 1 minus cosine beta. But even moderate angles, so 150 degrees, so I got deflected by 30 degrees essentially. That's large enough where I'm not going to impact the jet coming in. Still gives me 1.86 for 1 minus cosine beta. Comparing to 2, that's not that bad, so only 7% less. So still get a pretty good amount of energy compared to the maximum anyway, even with a 30-degree deflection. In terms of the bucket or blade speed and rotational rate of my turbine, the maximum power actually occurs if my wheel, the buckets on there, their linear velocity is spinning at exactly half the rate of the velocity coming in. You can find that through differentiation. So if you take the shaft work equation from the previous slide, take the differential of that with respect to u, you'll find that that occurs, obviously, again, derivative with respect to u equals, set that equal to 0, solve that for u, gives you where the maximum power happens, and that's half the incoming velocity. So we've spoken a lot about water wheels. Another common form of an impulse turbine is something like a dentist drill. This guy uses air instead of water. So they have these nozzles that are kind of pointed towards these vanes. And so here's basically your impulse turbine, like the water wheel we had before, but air coming in. Again, it's going to spin that around. So all this air hitting those vanes spins this around. This spins at a relatively high speed. Remember, if you've ever been to the dentist, makes pretty high-pitched noise, indicating a pretty high rotational speed. Again, when the air comes in, gets deflected by the vanes. Air speed doesn't really change, only the direction. And so again, this is an impulse turbine. So the dentist drill is actually an axial flow device. I have this air coming in, hitting these vanes that spin around. So air coming in this direction, comes out in that direction. So again, change of direction gives me the impulse turbine, not necessarily change in speed. The other type of turbines are reaction turbines. These are kind of like my centrifugal pumps, but again, backwards. I have this rotor surrounded by a casing. So again, a lot like what a pump would look like, but a pump, fluid comes in, pump spins it around and shoots out the side. Here I have the opposite. I'm coming in the side. It's spinning this thing around and being shot out axially. So you get both a pressure drop and a velocity change across these rotor blades. So these guide vanes act as nozzles to accelerate the flow. I have part of the pressure drop across the rotor itself and part of it across these vanes that are accelerating the flow. Again, similar to a pump in reverse, generally have low head, high flow rate devices. So in the impulse turbines are generally high head, low flow rate. Reaction turbines are the opposite. Typical radial and mixed flow. Liquid turbines are called transit turbines. So again, we can have radial, mixed, or axial. So the radial and mixed versions are called transit turbines. For low heads, most efficient turbines are axial flow or propeller turbines. These are generally Kaplan turbines. So you can see the difference. This guy here being a transit turbine. This guy here being a Kaplan turbine. Radial flow turbine, fluid leaves only a small tangential component of velocity. So again, I have a velocity change in terms of speed as well as direction. So basically taking a lot of that energy out in terms of kinetic energy. Impulse turbines have the same speed in and out, it's just the direction that changes. Reaction turbines also slowing it down, so taking out more energy from that. So angular momentum being reduced, that again does more work, taking more energy out of the fluid. Again, same general equations for shaft torque and shaft work. M1 dot R1 v theta 1 going in, M2 dot R2 v theta 2 going out. Those guys times omega, so R becomes U for the work part of it. In terms of turbine performance, it's going to look very similar to what we had for pumps, because again, it's just basically pumps in reverse. So I still have the same dimensionless parameters. My flow coefficient CQ, which is the flow rate Q divided by omega d cubed. I have the head coefficient CH, which again is G times H over omega squared d squared. The power coefficient, W dot shaft over rho omega cubed d to the fifth. Again, all the same as what we had for the pumps. The one difference though is the turbine efficiency. So for pump efficiency, well, any efficiency really is energy out divided by energy in. For the pump, the energy going out was added to the fluid. So rho GH times Q was the energy out, W dot shaft was being put in. Here for turbines, I'm getting shaft work out, putting in energy from the fluid. So what comes out in this case is W dot shaft. What goes in is rho GQH. So basically exact opposite, flipped upside down or inverse of what we had for pumps. And similarly for pumps, we have all those other dimensionless parameters that we're not going to worry about because some of them deal with geometry and we're assuming we have geometric similarity. Other ones like your Reynolds number are still going to be high. So still having a relatively high Reynolds number means that guy's not really important, doesn't affect things too much. So again, the head coefficient, the power coefficient, and the efficiency all really just depend on this flow coefficient CQ. Again, same as what we had for pumps. Pump selection purposes, whether to use axial, mixed, or centrifugal pumps, do the same thing for turbines. We have a power specific speed, so NS prime. So the prime is for my turbines essentially as opposed to my pumps. These guys, what I care about is the shaft work. So officially, the dimensionless version of this, I have omega square root of shaft work over rho over GH to the 5/4 power. Gives me a dimensionless number for the power specific speed. And that's the actual dimensionless version. There's also a common US version that is dimensional, so not dimensionless, but does use standard units, so it makes my life easy when it comes to calculating these things. So omegas and RPMs. I have shaft work in horsepower. Get rid of the rho, don't need it. Get rid of the G on the bottom, don't need it. And then HA in feet to the 5/4 power. And that gives me the dimensional version of specific speed. And from that, I can compare efficiencies for these various different turbines. So impulse, maximum efficiency, down around 5 for a specific speed. The Francis turbines, generally in the range of 20 to 60 or so. And the Kaplan turbines, somewhere around 100 is their peak efficiency. So again, depending on what specific speed what actual application the pump's going to be, or the turbine will be used for. I can see where that falls on this chart, and I know which is the appropriate turbine to use for that application. And last thing, pumps and turbines generally opposites of each other. One adds energy, one removes it. Some turbines can be run in reverse and used as pumps, and vice versa. Some pumps can be run in reverse as turbines. That happens at some hydroelectric power plants. Turbines providing power during periods of high demand. So again, these hydroelectric power plants are generally dams. You have a big turbine in there, so as water comes down over the dam, it spins the turbine. So when you have high demand, you have that thing turned on. When you have low demand, though, you might not need it. So what you do is you take that extra energy and you actually turn that turbine into a pump and actually pump the water back up so you can use it again the next day during high demand. Again, it's not the case for all pumps or turbines. Water wheel, can't run that in reverse because it just doesn't, it's not very efficient. So example, an impulse turbine shown below, basically just a water wheel if we had. This guy's 85% efficient, so in terms of the shaft that it's attached to, I can get 85% of that power out of it. Assuming the resistance of the penstock is this pipe down here. So friction factor for this guy is 0.015. Head loss in the nozzle, so again I have a nozzle out here. So I have this 1 meter diameter tube of water, and then I have a jet basically to increase the velocity so that when the velocity hits here, it's going faster. It's going to give me more energy and therefore more power. So assuming there's no head loss in that contraction. Ideal conditions, so my buckets, this rotational speed here is half of the jet velocity. One on what power developed by the turbine. So how much power am I getting out of this? One on the angular speed of the wheel. And then finally, what torque is exerted on the turbine shaft. So you can have some big dam, water at some elevation of 1,670 meters. This 6 kilometer long pipe, diameter 1 meter, jet, diameter 18 centimeters, 3 meter diameter water wheel at an elevation of 1,000 meters. How much power am I getting out of that? You can obviously not draw on scale. So energy equation between the top of the water and the point where the jet hit the turbine. So basically point 1 up here, point 2 right where I'm hitting the bucket here. So it's a standard Bernoulli equation, P1 over gamma, V1 squared over 2G plus Z1. That's everything on the left-hand side. Point 1 is P1 over gamma, V2 squared over 2G, Z2, and whatever head loss I have between point 1 and point 2. So P1 up here is atmospheric, P2 down here is also atmospheric, so those guys go away. My dam is a pretty big body of water, so this is not going to go down very fast. So V1 is approximately 0. And then Z1 minus Z2, so 1670 minus 1,000, elevation gain of 670 meters. I have this head loss equation, F L over D, V3 squared over 2G. So again, V2 is coming out of the jet. That's a different velocity than what's actually happening inside my pipe. So I'm calling the velocity inside the pipe V3. So plugging all that into Bernoulli's equation, I have Z1 minus Z2 is the velocity V2 squared plus over 2G plus this head loss, F L over D, V3 squared over 2G, everything else is gone. And then V3, I know it's related to V2 due to conservation of mass. So V3A3 is V2A2, which means that V3 is D2 squared over D3 squared times V2. And then I know the diameters, 0.18 meters for D2, 1 meter for D3, gives me V3 is 0.0324 times V2, it's roughly 3% inside here. Much bigger pipe, obviously. I can solve this previous equation. So this guy here, plug this in for V3, and then solve it for V2. And I get the V2 squared is 2G Z1 minus Z2 over 1 plus 0.0324 squared FL over D. I know all these numbers. So G 9.81, elevation change 670, 1 plus 0.0324, that's from my velocity conversion, square that. F was 0.015, length 6 kilometers, 6,000 meters, diameter of 1 meter, gives me a V2 velocity of almost 110 meters per second when my water is hitting my turbine water wheel. Then define the power. Power is flow rate times gamma times head. So flow rate is V2 times A2. Gamma is just gamma. And then my head, again, I want everything to be converted into velocity. So I assume that everything was converted into this V2 squared over 2G velocity term. And so putting that all together, I have pi d squared area. Gamma is rho times G, specific weight. So the G's cancel out. That just leaves me with a density. I have velocity squared and another velocity, so velocity cubed. And then my area, I had a pi over 4 times d squared for the area. So the 4 came down, it makes that a total of 8 with that 2. So plugging the values in, pi, diameter 0.18 meters squared, density of 1,000 kilograms per cubic meter, velocity was 109.3, cube that divided by 8, gives me 16,750 kilowatts for this turbine. But since it's only 85% efficient, so that's how much energy is being produced at the bucket essentially. So 85% efficient means the actual power produced, 85% of that is just over 14,000 kilowatts in this case. So that's the answer for part A. Part B, I want the tangential bucket speed. I know that we have the ideal conditions. So for ideal conditions, the bucket speed is 1/2 of my jet velocity, V2. So 1/2 of 109.6 meters per second is 54.8 meters per second as the tangential velocity of the bucket. You can then find the angular velocity by taking that tangential velocity, dividing it by the radius of the wheel, which is 1.5 meters. And that gives me an angular velocity of 36.5 radians per second, or more standard units in RPMs. Just make that conversion. So 1 revolution over 2 pi radians, 60 seconds in a minute, gives me 349 revolutions per minute for that water wheel. And then torque related to power. Power is torque times rotational speed. So torque is power divided by rotational speed. I know the power from part A, 14,240 kilowatts. I know the rotational speed from part B, 36.5 radians per second. And that gives me a total of 390 kilonewton meters for the torque. So that was the last lecture for the course. Hope you enjoyed it. Hope it wasn't too bad. Hope the course overall wasn't too bad either. So be sure to get the homework in before it's due. Be sure to do the exams before they're due, and feel free to stop by my office hours or email me for any other questions. Good luck with everything, and I may see you in a future course.